Today we're going to talk about composite failure rates, when to use composite failure rates instead of generic or specific failure rates in general. For those of you that do not know me, my name is Lauren Stewart. I'm a CFSE here working at Excida. I work mainly with our mechanical customers. I either help customers with their certification to get IEC 61508 certified. I also do a lot of our training and help end users use those certified products. I see a couple of new people on the webinar today, so I'm going to introduce Excida quickly. I like to say no matter where you are or where your company is or where your customers are, we have someone close by to help you with any of your functional safety needs, whether that is functional safety or alarm management or cybersecurity. We have experts in the field close by to wherever you may be. If you are not familiar with Excida, you might have not know about Excida at all, or you might have just heard about one or two of our industry focuses before. But Excida is actually involved in the complete supply chain of functional safety in multiple industry sectors. So from the OEM who require the product certification through to the end users that use that product, that certified product. Excida can help with software. We have tools, we have training, we have consulting to help make your job easier. I mentioned a little bit about our consulting services. We have engineering and consulting services, not only in the process safety or functional safety, which you might be more familiar with, especially if you're on this webinar, but we also have it in alarm management and cybersecurity. So we are able to help with the complete life cycle of functional safety. I mentioned quickly earlier our tools, but I'm going to show you a couple examples of our tools later on in this webinar. So I'm just going to introduce them quickly now, but we have a suite of engineering tools that were really designed to save you time and money. They can do that because they increase your efficiency and your productivity. So if you're trying to perform PHAs, LOPAs, SIL verifications, which we're going to look at Excelencia in the SIL verification portion of it today, or if you're trying to do proof tests, SRS creation, even alarm rationalization or cyber risk assessment. We have tools to really make your job in functional safety easier. We're also going to talk briefly about Excida certification, where some of the failure rates and numbers come from. And we have certification, not just in the IEC 61508 certification that we'll be talking about today, but we also have certification in IEC 61511, ISO 26262, cybersecurity certification, machinery and personnel certification as well. So if you want more information on Excida itself, come back to our website, take a look at it, or email us directly and we can get you into the contact with the person that would be best. But let's go ahead and talk about why we are here today. Composite failure rates. We're going to look at some best practices in SIF verification and really answer the questions, when do you use composite failure rates? When do you use generic failure rates? When do you use a specific failure rate? What are the combinations and what's the best for you? Like I said earlier, we're going to pull up Excelencia and actually look at the SIF verification in the tool itself and show the difference on the PFD and the probability of failure on the SIF in different examples. So let's go ahead and get started. I kind of like to take things back to the beginning on my webinars. They're normally a large group of individuals with varying degrees of functional safety knowledge, but I'm going to quickly start explaining why it's important to get the correct data in SIL verification. And that all comes down to what is SIL? And we all might be familiar with SIL and why it's important, but it comes down to it was listed in the standards. It was brought forth by IEC 61508. If you're familiar with that, some people call that the grandfather clause or the standard or the umbrella. It covers everything in process safety and functional safety. It really is applied to the suppliers, anybody that is building the parts and want to get their parts certified. Underneath IEC 61508, we have more specific standards. Instead of the umbrella or the general standard, you have a standard specifically for the process industry if you are using those certified products, IEC 61511, or if you are doing machinery. There's a special standard for you. Nuclear, there's a special standard for you. However, if you don't have that special standard, the IEC 61508 will cover you. In not only IEC 61508, but IEC 61511, it defines SIL as your safety integrity level. And there are 4 SIL levels, 1 through 4, 1 being your lowest, where 4 is your highest. With each level, there are more requirements and a more justification needed to prove that you are at a higher level. So every time you move up a SIL level, you not only need to do the requirements from SIL 1, you need to add extra SIL requirements for SIL 2, and so on, until you get to your highest level, SIL 4. One thing to note in IEC 61511, it really only defines SIL 1 through SIL 3 for the process sector, except for nuclear. If they say, if you find yourself in a SIL 4 situation, refer back to those details in IEC 61508. Once again, being that umbrella standard. And your safety integrity levels or your SIL is really a merit of how well your SIF is performing its job, how well your SIF is going to manage risks. So knowing that your SIL is showing how great you're doing your job or how poorly you're doing your job, it's important to know how SIL is used. And there's 4 main ways that you use your SIL level. You can establish risk reductions by your SIL level. You can establish your architectural constraints. You can establish your systematic capability, and you can establish your probabilistic limits for hardware random failures. And we're just going to quickly explain what each of these 4 mean before we get into our examples in our SIF verification. So the first way you use your SIL is to establish risk reduction. I like examples. That's the way I learn best, so I tend to use them a lot in my webinars. So this first example is showing risk reduction. Let's say you have your PHA and it determines some specific hazard can occur every 10 years, and that would cause a major release of toxic fumes into the atmosphere. Well, you need to come up with some risk reduction factor to take that hazard to occur once in every 10 years to once in every 500 years. You've determined that was a much more acceptable time allowance, so you need to reduce your risk. You simply divide the 500 years by the 10 years, and you have your risk reduction factor of 50. Once you have your risk reduction factor, you take that, put it into the table in your IEC 61508 and IEC 61511. You can see you have a risk reduction factor, an order of magnitude, and it matches up with a safety integrity level. With, once again, each level of increase, it's a level of increase for your risk reduction factor as well. So SIL 1 being your lowest, SIL 1 being your lowest risk reduction as well. And each SIL level you increase, you are bumped up an order of magnitude in your risk reduction. The second way you can use your safety integrity level is to figure out your architectural constraints. And architectural constraints was put into place to provide a minimum redundancy requirement to really protect against bad failure rate data or unrealistic proof test intervals, just unrealistic data being used. It's kind of, I call it a sanity check. When you are designing a SIF, you must comply with one of the specified charts in IEC 61508. There are two charts or two routes that you can take, either Route 1H or Route 2H. Both of these are defined and laid out in the standard. Route 1H involves calculating your safe failure fraction. And that's not just your safe failure fraction for your device, it's your safe failure fraction for your element or your SIF. You want to take a look at your failure rates for your safe detected, your safe undetected, and dangerous detected failures, and compare them to your overall failure rate. The main difference being adding in those dangerous undetected failures. And that's going to give you your ratio of safe failures compared to your total failures. The alternative route is Route 2H. Route 2H, instead of doing your safe failure fraction calculation, you throw that out the window, but you are saying that you have a high confidence in your data quality or your data collection. And this isn't just, oh yeah, I kind of feel good about it. No, this is actually, you have a 90% or greater confidence factor in the results of your data quality and data collection. So what do you do now that you either have your high confidence factor or your safe failure fraction numbers? You then, once again, go to the tables in the standards. There are two different tables. Well, there's more tables than that, but per Route 1H or Route 2H, there's different tables for you to apply. If you are doing Route 1H and you're doing your safe failure fraction, this is the example of the type A 1H table. There's also, this is for simple mechanical devices such as valves or actuators, but there's tables specifically for your smart devices as well. But you can calculate your safe failure fraction, and knowing how much redundancy, or you can pick your SIL level that you need to be, or you pick your SIL level you need to be and pick your architecture from there. The hardware fault tolerance in the architecture allows extra sets of equipment to do the same job. So if you have a hardware fault tolerance in this table of 0, there's no extra set of equipment. If you have a hardware fault tolerance of 1, you have 1 extra set of equipment. That might be a 1 out of 2 or a 2 out of 3. On the right-hand table, you have your 2H tables, and this is kind of a simpler table. You don't have to do your safe failure fraction calculation, and there aren't different type A, type Bs. This is simply in low demand mode or demand mode of operation. This lets you know if you want a SIL 1, you don't need any redundancy. Same with SIL 2, but if you are going to be a SIL 3 application, you need at least 1 extra set of equipment. SIL 4, at least 2. The third way to use your SIL level is to judge your systematic capability. If you have seen certifications, this is just the middle of an Exceda certificate, you might have heard the term systematic capability before. Well, what does that mean? Well, systematic capability is really the evaluation of a quality management system per all of the requirements of IEC 61508. If the quality management system meets all of the requirements, then a SIL capability rating is given to that product. And that's one thing, the wording is a little confusing. It talks about being SIL capable. Since there's so many things that go into your SIL level, we cannot just say the device is. But this lets you know what the device can go into. This is your limiting factor. So let's take, for example, you need a SIL 2 application. You must use a SIL 2 device or above a SIL 3 device. You cannot use a device in a lower systematic capability rating. So in your SIL 2 SIF, you cannot use a systematic capable if only a SIL 1. So remember your systematic capability, whether it's written out or on the logos, that's going to be one of those limiting factors for you. Finally, the fourth way to use your SIL is one of the most important ways is probabilistic limits for your hardware random failures. Well, what exactly is that? That's a mouthful. That means your PFD average, your random failure probability. What are the chances that if a demand on your system is going to occur, it's going to be a dangerous demand? This is going to be based on multiple, or on an equation with, it can be simplified, it can have up to 10 different variables in it. But just like the other tables, you have your PFD average, and well, if you're in high demand, you'll also have PFH tables. However, your PFD average tables will once again line up with your safety integrity level, and each safety integrity level will be an order of magnitude increase. Once again, your SIL 1 being the lowest, SIL 4 being the highest. I talked about the PFD average being a calculation, and this is a very simplified version of the calculation. This only takes in consideration 4 of the possibly 10 variables, but even in the simplified calculation, one of the most important factors in your PFD average calculation is your dangerous undetected failure rate. And that dangerous undetected failure rate where does that come from? That will be those failure rates for the safe failure fraction. And we talked about that comes from the back of the certificates, and that comes from the FMEDAs. If you've not heard of an FMEDA before, an FMEDA is a failure mode effect and diagnostic analysis. And an FMEDA is a detailed analysis of a specific device, and we look at every single component in that given design, and look at every way that component can break. We'll look at the different stress levels of that specific design versus the stress levels of the application and the environment. And when you are done with a Femina, you are given your failure rates. Once again, that's what's on the back of the certificate. That's what goes into your PFD average calculations. The Femina technique has been was actually created in 1999, and it's been constantly calibrated from that point on. And we like to call it a calibrated Femina approach. We do that by constantly analyzing our Femina database with field failure data and manufacturing databases as well. And we're constantly comparing that and calibrating the database. The Femina approach will not only give you your failure rates that we talked about that were so important, but they'll also let you have your product failure modes and also your diagnostic coverage. So when you are finished analyzing the Femina, this is one of the examples of what it might look like. This is what that back of the certificate will look like, or the Femina report would look like. This is an example of a valve. But as you can see here, the failure rates are given for a specific device or specific design in a specific application. So it's open on trip, full stroke, tight shut off, and also the operating conditions. You're going to look at if it is cabinet mounted or subsea, if it is going to be clean service and just have lovely water going through, or if it's going to be a severe particle, dirty, corrosive sludge going through. And an FMEDA can take all of that into consideration. When considering using an FMEDA or the failure rates from an FMEDA, one thing that you really have to be conscious of is the component database that was used to produce that FMEDA. I always like to say, make sure you're comparing apples to apples. Make sure you're comparing a component database from a similar application, a similar environment. If you are a valve that's cabinet mounted in a temperature controlled setting and you have clean water going through you, you don't use the same failure rates that you would get from Arita. Arita, if you're not familiar with it, is a fabulous reliability database that is off of the offshore from the North Sea. And they have both offshore and subsea. Like I said, make sure you are comparing an apples to apples comparison, not only environment, but application as well. So now you have your failure rates for each device, your sensors, your logic solvers, your valves, your actuators, your solenoids. Let's put them together and make a SIF. And let's take a look at some, I told you we'd show some tool snapshots. So let's show Excelencia and put together a SIF, and let's look at some examples. As I said, this is our tool, Excelencia. I put together a specific SIF. I wanted to show you what it looked like if we chose, in this example, a specific sensor, specific logic solver, and a final element consisting of a specific valve, actuator, and solenoid. When we put together our SIFs, I took into consideration pretty normal conditions, nothing crazy with proof tests or emission time, just some typical constraints, and I came up with some typical results as well. Our PFD average for our sensors is 3.49 times 10 to the negative 4. Logic solver, 1.89, 10 to the negative 4. And our final element is 7.2, 10 to the negative 3. Our final element's taking a little bit more of our PFD average, which is expected. If you put our SIF together, we are achieving a SIL 2 SIF. That might be exactly what you want. That could be wonderful. However, what if you're not sure which exactly sensors you're going to use? Let's keep everything the same. Besides that, let's keep the logic solver the same, the final elements all the same, but just switch out your sensors for some generic numbers. When you switch out to generic numbers, you're obviously going to have to, they're going to be higher. You don't know exactly what you're going to be picking, so they're going to be more conservative, and that has to be expected. Everything else being the same, our PFD average of our sensors is going to now overshadow our final elements, and unfortunately, we are now down to a SIL 1. Now wait, there are things you can do to bring that SIL back up. You can adjust other variables in your PFD average calculation. Remember earlier I said there's a possibility of, if you're considering everything, 10 variables. So you can switch something like your mission time or your proof test interval or your maintenance activities. But before you do all that, first ask yourself, is that really necessary? Well, do you really need to be using generic in your calculations? Could you be using something like a composite failure rate for your device options instead of a generic? What do I mean by this composite failure rate? Well, composite failure rates started really when, if you're at a company that might have a list of preferred vendors, and let's say for our pressure transmitters, you might have these 3 pressure transmitters, and you're attempting to design your SIF. You want to look at your preferred vendors, and well, there's 3. Which one am I supposed to use in my SIL calculations? Well, if there's a clearly more conservative option, well, you can pick that one and know that the other 2 options would be less. But what if there's not a clear conservative option? Well, the next best option would be to consider to make a composite. Look at all of the devices that you have on your list or that you could consider and make your own composite, make your own list. All you have to do is simply list all of your options, whether it's 2 devices or 20 devices, and list out every failure rate per failure type that is going to be important for your application. So for pressure transmitters, you can see we have some failure rates that you wouldn't necessarily see on a valve, such as your low or your high. And list out all of the appropriate failure rates and pick the highest on each. So, for example, when we put our composite pressure transmitter together, let's look at the failure rates in our low category. The highest one is 52. Let's have that for our low. What about high? The highest would be 87 fits. Great. What about for the detected failures? 622 fits. Okay, let's put that down. What about for your dangerous undetected failures? 75 fits. And your safe undetected failures. Now that would be 81 fits. Now you can take this composite, the 52, 87, 622, 75, and 81, and make your own, enter your own data into exSILentia and put that into your sensor for your SIL verification. Now, before I show you what that looks like in exSILentia, first thing to notice is if you ever want your composite to be lower, you just simply eliminate something that is the highest in that category. So say, for example, in this composite, maybe you're very concerned about spurious trips. You don't want your plant shutting down. Maybe that's one that you would consider taking the spurious trip, the highest spurious trip, and eliminating that option. What if your dangerous undetected failure rate, the one that controls your PFD average, what if that was your main influence? You might want to eliminate that one. So you can always change your composite if you need to eliminate some of your choices if you need to after you come back and do your SIL verification. But let's take a look at that. So you can, up in the corner, top corner, you can see instead of picking a device, now we're going to do user define, and you're going to add your own data in. And you're going to add those numbers straight from the composite numbers that we just calculated. Add them for your fail low, fail high, fail detected, dangerous undetected, and safe undetected failure rates. And then all of a sudden you can see we are back to a SIL 2. So if that was your original goal, this might put you into playing field without having to select your final option. Always keep your composite failure rates in the back of your mind, especially if you're in the beginning of the design and you don't need to make your selection yet. Keep your options open. So what are some companies missing? Well, one of the premises of IEC 61508 and 511 is that the automatic protection systems with diagnostics and periodic testing can provide higher safety reliability than typical control functions. And the standards outline steps that must take place to be able to claim higher safety. However, these steps are only valid or appropriate if good or valid data is used. So what does this mean? Once again, we just zoomed in on exSILentia here. Don't just run your SIL verification with your composite numbers and just assume that you are good to go. Always do a sanity check as well. This is my last two examples for you, but always be weary of optimistic data with failure rate data as well. So take example, we have our SIL, we have our sensors, our logic solvers, and our final element together. And we are achieving a SIL 2 with no redundancy and no diagnostics. You might think that this is wonderful, this is great. For your final element, your valve, solenoid, and actuator together, you might think that these are the best products ever because they are only 12 fits. So the mean time to fail would be almost 9,500 years. How does that sound? Huh. Let's look at that differently. Let's say you have 9,500 of SIFs in your plant. Are you only going to have one failure a year? So always question, no matter what data, what failure rates you receive, always question it. Does it pass that sanity check? So I kept everything the same, except I changed out realistic data for your final elements. And as you can see, the safety integrity level dropped. Once again, like we talked about earlier, there are things you can do. You can implement diagnostics. You can help your maintenance, shorten up proof testing or mission time to get a better PFD average. So don't just fake it. You can achieve your good results with using realistic data. So what we want you to take away from this is, if you know exactly what what devices you're going to use, go for it. Use that data if you have the failure rates in your SIL verification. However, there's lots of times where you don't have that information or you haven't narrowed that down yet. Maybe instead of using generics and really skewing your SIL verification numbers, use composites, as long as your composites are going to be realistic. Open up more opportunities for you, and really be seen as a leader by using those composites instead of just eliminating options right off the bat. I'm going to go ahead now and take some questions. If you think of questions later on, please feel free to email me. There we go. Okay, so we have a couple questions. The first one, it was about the 2H, the 90% confidence data quality. We had a couple questions on 1H and 2H come in. So 1H is the approach of using your safe failure fraction, and 2H is that kind of that proven in use historical method. If you use the proven in use method, you have to have high confidence in that data quality. As I said, that's just taken straight from the IEC 61508 standard. It lets you eliminate the safe failure fraction calculation. This is especially good if you are a simple mechanical device. Safe failure fraction is great if you have safe failures or diagnostics. However, if you're a simple valve or an actuator, you don't necessarily have the smarts to have a lot of safe failures. You're not going to have a lot of self-diagnostics to help with that. So your safe failure fraction would be a very low number. In that, you can show historical records and historical data, as long as you're keeping those records and data, to get around the safe failure fraction. And for those of you that are asking questions about 1H and 2H, we have webinars on just those topics. If you go to our YouTube channel or our website, you can, we have some great webinars on 2H and comparing 1H versus 2H as well. The next question, can I use two SIL 1 items in order to achieve a SIL 2 rated loop? No. That's a great question. That is, when I said that's your limiting factor, that's exactly what I meant. Your systematic capability, you can never go above, no matter how many of them you put in there. So your systematic capability is that limiting factor. You can put anything, you can put a higher systematic capability in anything lower. However, you can never put, if you put 2 or 3 of the lower systematic capability, it cannot make up for the higher systematic capability requirements. We have a question on dangerous undetected failures, asking if they are all failures not detected by automatic diagnostics. That's not necessarily true. There can be the dangerous undetected failures. Well, all of the failure rates are evaluated by the FMEDA. It depends on how each component can break, where the stresses and strengths are of that component, and adding those up with the diagnostics into consideration, such as partial valve stroke testing or full diagnostics. So to get the dangerous undetected failure rate, you would have to go through a full FMEDA. This goes back to, I believe, the composite failure rate. How can there be such a wide range of dangerous undetected failures? Well, just because we listed 3 pressure transmitters doesn't mean that they were 3 similar pressure transmitters. You could have a lot more components, a lot more diagnostics. You could have a lot more parts and complexity. So just saying a pressure transmitter should have similar dangerous undetected failures. You need to look at more than just what that is. I would suggest, if you're comparing the failure rates, looking at the FMEDA reports of each to see exactly what diagnostics and everything has been considered. The next question, what is the residuals or no effect impact of the PFD average? Well, the residual or no effect failure rate does not have an impact on the PFD average calculation. The no effect or residual failures, even the external leaks, are just to let you know that they're there. And that could be if you have a toxic process, you want to know if something is leaking. You want to know, it might not prevent the valve from doing its job or the actuator from doing its job. It might still be able to close. However, you would want to be aware of a leak. The next question, how could you select a systematic capability for the composite? That is a great question. What I would do was take a look at everything you're comparing for your composites and see if they are all certified. If they're all certified devices, that's easy. You just take, once again, your weakest link or your lowest one and use that as the conservative approach. If they are not all certified devices, that could be different. that might answer if you want to be using them in your SIF. You can always do a different proven in use approach, but that's going to take a lot more time and constraint on you yourself as an end user. We have a question about redundancy. If SIL2 is only achievable with redundancy, and that's not necessarily always the case. You're going to have to do a detailed look at the SIF the SIF verification, kind of like we did in the Excelencia examples, to see exactly where you fall with redundancy. If you were meaning my example specifically, no, you can achieve SIL2, especially SIL2 with, or SIL1 without redundancy if you have the right devices in the right application. We had a question on the North Sea equipment failure rates that I was speaking of earlier. I was talking of Arita, and they are they publish the offshore and onshore reliability database collection every couple of years. The most recent one was published in 2015. They have a great collection of reliability data as long as you're doing an apples to apples comparison. So make sure if you're going to use that data, that it is your exact application. The next question we have, there are a lot of certificates. Does IEC 61508 require certificates for failure rates? Not for failure rates themselves. The failure rates come from FMEDAs or other processes. The certification process also takes into consideration that quality management system. The failure rates would not take into consideration that. So you could have an FMEDA on a product that is not a certified product. We have a question on how many components would you typically use in a composite failure rate calculation, and that's typically up to what you use in your system. If you have 2 vendors, 3 vendors on your supplied vendor list, I would use them all. So you have all of your options open when it comes down to that. However, if you have maybe 7 or 8 supplied vendors and you want to narrow down your list, that's could be understood. We usually see composites. I see composites with 2, 3, 4, somewhere around there. It just depends on what's going to make your life easier. The next question we have is about safe failures. Sometimes in the safety manual it says 0 for safe failure rates. Is that because they're not really safe failures? The chances are it is a simple mechanical device, and those safe failures, think of how it's in an application. So if you have a valve, let's say your safe failure would be a spurious trip. Maybe the valve closes when it doesn't need to close. What is going to make that happen? If you don't have internal diagnostics, a lot of the times you're not going to have a lot of safe failures. Once again, if you have a simple mechanical device, chances are you're not going to have a lot of those. We have the next question about when we put together the composite failure rate, asking if it is always going to be the highest failure rate of the group of components. And yes, especially when you're dealing with functional safety, you want to calculate your SIF as kind of your highest level. You don't want to calculate a SIF and find out that you're not running as safe as you were calculated to be. So when we talk about being conservative, when we talk about picking the highest number, it's so your calculations are going to actually cover the real world situations and not just going to be this unrealistic. Okay, we have another question coming in. Asking what kind of assumptions are made when Excida certifies for a SIL capable device. And I'm actually going to refer you to some webinars on just that topic. They're hour-long conversations on just that. We go through the standards and pick up all of the requirements that the standard says are required for that type of product. For that SIL level, and we make sure that the quality management system and everything that the manufacturer is doing is meeting all of the requirements in the standard. So for each SIL level, there's going to be more requirements. We have a question on finalizing SIL verification calculations from using data banks without certification from vendors. That's totally up to you and if you feel comfortable doing that. It also depends if you have a third party coming in. I don't know exactly your situation. I know if as a third party, sometimes we come in and do SIL verification calculations and we verify them. When we go through them, if unrealistic data is used in the calculations, we make the SIL verification be reran with better and more realistic data. So if you don't have certificates, you would need to do the more proven in use justification. So you would need to do the 2H justification type stuff for the quality management. It's definitely doable, but it's a lot more work. I have a question. I don't think I'm quite getting the point of the question about adding another SIL level. To add another SIL to reduce the SIL level that you can't meet. I'm not quite sure what that question means. If you feel, if you want to reword it, please feel free to email me later. Thank you for all of the questions coming in. I think I got them all. They were coming in kind of quick, so if I missed any, please feel free to email me. And thank you so much for joining me today. I appreciate it. And always find more information on, if you have more webinar topics that you'd like, send us ideas and come see our other future webinars. Thank you very much and have a great day.